Okay, so we just finished talking about one type of vector product, namely the dot product. And we saw, just by way of review, okay, U dotted with V, of course, is U1, V1 plus U2, V2 plus U3, V3. But then we also came up with an alternative form of the dot product that was by itself very helpful, right? It was the length of U, length of V times cosine of the angle between U and V, yeah? And that helped us to realize that what the dot product is actually telling us, which is what we suspected all along, was that it was detecting whether vectors were tending to aid one another or help one another or oppose one another. And the sign of the dot product would tell you that. If the sign was positive, then these vectors are tending to help each other. If the dot product is negative, they're tending to hurt each other. And if the dot product is 0, what did that tell us? What if the dot product is 0? What's true about the vectors? Well, no, there would be an angle between them. If the dot product is 0, 90 degrees. They're either perpendicular to one another or one of the vectors is 0. Either way, we say that the vectors are orthogonal. So orthogonal actually includes vectors being perpendicular. We saw the connection of dot product to work, yeah. And what else did we see? We saw the connection of dot products to not just work, but vector projections, right? And trying to understand forces through vector projections, okay? And we had this formula, the projection of vector U onto vector V is equal to U dotted with V over V dotted with V times V times the vector V, okay? So it's that scalar times that vector V, okay? So that was the formula for vector projection. And we looked at work, and we did some examples in that vein. Today we're going to start looking at a different kind of vector product, okay? The dot product, when I took the dot product, the output was a number or a scalar, yes? This product that we're going to come up with is actually going to be a vector itself, okay? And it's going to be a vector that tells us something about the vector that we started with, okay? And that's this thing called the cross product. Cross product. Now, I know that in physics, you are introduced rather quickly to both of these. How many of you have at least seen the cross product concept before, okay? Comes up quite a bit. It's very useful. But in the end, what we try to do is described right here geometrically. Okay, so I want to give you an idea of the geometry of what the cross product is doing. Okay, now I tried to make this little three-dimensional picture right here. So this is supposed to be kind of coming out of the board at us. Do you see that? See vector U kind of coming out of the board at us, and V's. Well, I guess U is basically parallel to the screen, and V is going into the screen, if you will. Does that make sense? Okay. And U cross V, by definition, this is the geometric definition of the cross product. U cross V, and you use this little symbol right here. It looks like an X or like a time symbol, is the vector. So first of all, what's the output of the cross product? I use the word vector. This product is actually going to deliver a vector output, whereas the dot product delivered a scalar output. So it's a vector that is orthogonal to U and V with one additional property. The length of U cross V needs to be the area of the parallelogram determined by U and V. Okay, so here's Here's like, here's a copy of V put up here. Here's a copy of U put right here. And this area right here, the area of this parallelogram determined by the two, right? So A is literally going to be the length of the cross product. Okay, it's easy enough to simply say the cross product needs to be a vector that's perpendicular to both U and V, but we also encode information in the length of that vector itself. Does that make sense? So we want a vector that is both perpendicular to U and V simultaneously, but also whose length tells us something, namely the area of the parallelogram determined by U and V. Does that kind of make sense? So the length of U cross V is going to be the area of that parallelogram, and U cross V is going to be perpendicular to both. Now, here's the thing. How do I determine, because there's actually two options here for which way that perpendicular vector could point. Do you see what I'm saying? Either it's going to point up or down. We know what the length of the vector is. The length is going to be the area of that parallelogram. We've decided that. We just want that to be true. It turns out that happens to be very useful in a variety of contexts later on. We will be very thankful we chose that as our length of the cross product, okay? But that still doesn't tell me whether the vector U cross V is going to point like up in this case or down, yes? I still need to make that decision. So how do I decide which way this thing is going to point? Well, what you do, okay, and this is, believe me, this is important, okay? What you do is you read this vector from left to right, U cross V, okay? You read it from left to right, and that's important. You say U cross V. And what you do is you put your right arm, okay, and that's what I'm about to describe is the so-called right hand rule here. You put your right arm in the direction of the way that you read this thing from left to right. Okay, so you put your right arm in the direction of U first, okay? And then you turn your hand so that your fingers can curl towards the other vector, okay? So in this case, I would be putting my right arm this way, okay? Oh my goodness, I'm gonna try to draw it, but forgive me ahead of time. So I put my right arm in this direction, and I'm gonna put it so that I can curl my hands in the direction, I can curl my finger in the direction of V. Does that make sense? And then you say, now which way does my thumb point? Well, that way, right? Oh man, what am I doing here? Right, my thumb is going to point that direction. It points up. Do you see that? If I kind of make sure that my fingers are curling in the direction from U over to V, then my thumb points up in this case. Does that make sense? Okay. You put your right hand in the direction of the first vector in the product. You turn your arm, you rotate your arm so that your fingers can curl towards the other vector. Yeah? So right arm along U, I turn my hand so that I can curl it towards the other vector. Okay, and similarly, like think about it. If I read V cross U, where would I point my arm to begin with? If I read it left to right, I would point my arm towards what? V, and I would say, okay, now I need to rotate my arm so that I can curl my fingers towards U. And which way does my thumb point when I do that in this case? Down. You see it? Actually points down in that particular case. If I start with my arm towards V, I rotate it so I can curl my finger toward U, my thumb is going to be pointing down in that particular case, okay? That's called the right hand rule. And please, make sure that you use your right hand for the right hand rule. Believe me, I've seen it happen before where there's kind of a symmetrical, like they see me doing something and then they do it with their left hand out in the audience and they get the opposite result. Does that make sense? There's a reason this is called the right hand rule, okay? So once again, what is U cross V going to be? Well, the geometric definition, which is always kind of a good place to start, is that U cross V needs to be perpendicular to both U and V. That's number one. Number two, it needs to have length that's equal to the area of the parallelogram determined by U and V, okay? And number three, its direction, because now I can either go up or down. Its length is determined at this point. Its direction is determined by the right-hand rule, where we read the vector left to right. You put your right arm towards the first vector you read, and you rotate your arm so that you can curl your fingers toward the other vector. And wherever your thumb points, that's the direction of U cross V. Yeah? Okay? Any questions on that? Hopefully that kind of makes sense. Okay, but this is important. The length of this thing is going to be the area of the parallelogram determined by U and V. Okay? All right. Let's go down here. What are some properties of the cross product? Well, so obviously the length of the cross product gives us the area of the parallelogram, yes? And you guys know how to compute the area of a parallelogram? It's basically base times the height, yeah? Same as like a rectangle, except the height is a little bit awkward because it's not one of the sides of the rectangle, okay? Well, do you guys realize that the height of this thing, so let me just kind of draw, work inside of this picture. The height of this thing is going to be the length of V sine of theta, yeah? I would use the sine function. I would go sine theta. Okay, so if I call that length h right there, you know that sine of theta is equal to opposite, which is h, over the hypotenuse, which is the length of v. You see that? And therefore, h is equal to the length of v sine theta. Therefore, because the base length, I mean, think about it for a second. The base length of this thing, b, is just going to be the length of u. You see? Yeah? Therefore, what is the area of the parallelogram? Well, first of all, the area of the parallelogram is the length of the cross product by our definition, yes, by the way we have defined things. So the area of the parallelogram is base times height, which is going to be length of u, length of v, sine of theta. Doesn't that remind you of something? What was u dotted with v? What was u dotted with v? It was length of u times the length of v times what? Cosine of the angle between them. And it turns out that there's a nice parallel with the cross product. The only thing that's happened is that when we compute the length of the cross product, it's not length of u, length of v, cosine of theta. It's length of u, length of v, sine of theta. Now, it might bother you a little bit that there's a sine of theta in here because you would hope that the length of a vector is always positive. But remember, what is our angle always between? If I'm looking at the angle between two vectors, what is that angle always, what's the range or the possible values of that angle going to be? 0 to 180 degrees. Okay, 0 to 180 degrees. And what's true about the sine function between 0 and 180 degrees? Always positive, yeah? So that's fortunate for us for sure, okay? Now, okay, so this picture right here is just us sorting out a formula for the area of the parallelogram. That's the definition of the length of the cross product. But then we actually wrote down what that ends up being, length of u, length of v, sine of theta, okay? The second property is basically saying, hey, don't you see that, that if I do u cross v, it's the opposite of v cross u, yes? It is the opposite of v cross u, just by the right-hand rule, okay? That's interesting because all other products that we've seen up to this point in our career have been commutative. You know what I'm saying? It doesn't matter whether I multiply in one direction or the other. But with the cross product, it actually matters. You see what I'm saying? Like if I multiply in the one order versus the other, I get the opposite of what I got before, yeah? Okay, so that's an interesting little feature. Okay, u cross v equals 0. U cross V equal to 0, huh? What would that mean? Think about it for a second, geometrically. If U cross V were 0, what would that mean geometrically? If U cross V is the 0 vector, what would that mean geometrically in terms of the area of the parallelogram? This would mean that the area of the parallelogram is what? Equals 0. And how in the world would that happen? The vectors are right on top of each other or something. Does that make sense? So that would mean, you know, if this was U, okay, then V would have to be basically right on top of it. Okay, so this would be V, which means that V is basically some scalar multiple of U. Does that make sense? Yeah? So if the cross product is the 0 vector, that means that U and V are actually parallel to each other. Hey, that's interesting. What did the dot product tell us if it was 0? If the dot product of two vectors was 0, what did that tell us? Perpendicular. What does the cross product being 0 mean? The vectors are parallel. They're scalar multiples of each other, and therefore they're parallel. What if the picture would have been like this, by the way? What if it would have been U going this way and V going this way? Those are still parallel vectors, right? You would still have V equal to C times U. But what would the parallelogram look like there? It would still be a degenerate parallelogram. Do you know what I'm saying here? It would be a degenerate parallelogram. I mean, I guess I would try, I mean, look how stupid this is. I guess I might try to draw U right here, and then I might try to draw V right here. But the whole picture is collapsed in on itself. Do you see what I'm saying here? Yeah? The whole picture is collapsed in on itself, and I still get area 0. Yeah? So whenever V and U are scalar multiples of each other, I get a degenerate parallelogram and hence an area 0 parallelogram, which means the cross product is 0. Okay? Any questions on that so far? Questions? Okay. Some interesting little features falling out here. So what if I take a constant multiple of U cross V? Well, it turns out I can distribute that constant to either U or to V, right? And I would still get the same thing, okay, in the end. Okay. Next, what about a little distributive law? Well, we have one of those. Okay. U cross V plus W is the same thing as U cross V plus U cross W. Okay. So there's a little distributive law that still holds. What if I take the cross product of a vector with 0? What do you think I'm going to get? Well, excuse me, I'm going to get a degenerate parallelogram again. Yes? I would have one vector and I would have a degenerate second vector, and therefore I would get a degenerate parallelogram. So the area would be 0, so the cross product should be the 0 vector. Okay? So all of these properties are going to be brought to bear here at some point. So again, we have the parallelogram law, the fact that if you take the cross product in opposite order, you get a negative, the fact that U cross V is 0, precisely if they're scalar multiples of each other. We have a distributive law, and we have the fact that the cross product of U with 0 gives you the 0 vector. Okay? Now, you might say to yourself, this is all really nice, but what is the formula for U cross V? So is there a formula? Is there a formula for U cross V? Because it's all well and good to actually say U cross V is just the vector that whose direction is determined by the right-hand rule. It's perpendicular to both of the original vectors, and that has length equal to the area of the parallelogram determined by those vectors. It's nice to say all of that stuff, but is there an actual formula where if Daniel gives me one vector and another vector that I can actually compute it easily? Does that make sense? So I want an actual formula. I don't want to just talk about it in these like vague generalities. Okay? Well, let's think for a minute. Let's start with like the standard vectors. So first of all, what is the cross product of the standard vectors? Like I cross I. Well, I and I are obviously scalar multiples of each other, correct? Therefore, if I try to compute the parallelogram determined by I and I, it's a degenerate parallelogram, right? And I'm going to get the zero vector. Same thing with J and K. Yeah? Now, what about, okay, let me just sort of draw a picture here. What about I cross J? Okay, so think about it for a second. So here's I, all right? So here's I, here's J, and here's K. I want to compute some cross products, people, okay? So I, J, and K. Now, let me ask you a question. Let's think about the parallelogram determined by I and J. Okay, let's think about the parallelogram determined by I and J. Isn't that just a square? You know what I'm saying? What is the area of this thing? Okay, so the area is 1. Yes? And if I do I cross J, think about it. Which direction is I cross J going to point? You put your arm in the direction of I, which is kind of coming out of the board towards us, yes? And you, okay, you are actually, no, yeah, it's coming out of the board towards us if I'm looking at it the way that you are, yeah? And then you rotate your arm so that your fingers, your right arm, so that your fingers can curl towards J. Which way does your thumb point? Up, yeah? Therefore, I need to have a vector that is perpendicular to both I and J, which, by the way, something right on the z-axis would, yeah? Positive z-axis, needs to point straight up, and it needs to have length equal to the area of that parallelogram. Well, what is the area of that parallelogram? 1. Therefore, what vector am I talking about here? K. I cross J is K. Similarly, K cross I, if I put my right arm up towards K, and I put it so I can curl my fingers towards I, my thumb is pointing in the direction of J. You see that? K cross I should be J. J cross K, right? So I put my right arm towards J, I curl my fingers up towards K, my thumb is pointing towards the positive x-axis. J cross K is I. Okay, J cross K is I. Therefore, hey, let me ask you a question. What about J cross I? What about, okay, if I cross J as K, what's J cross I? I cross J goes one direction, J cross I goes the opposite direction. So J cross I is negative K. All right. What about I cross K? Negative J. What about K cross J? What about that? Well, it's negative I. You know what I'm saying? Yeah. So the I's cross, I cross with itself, J crosses itself, K crosses itself. That's the zero vector. I cross with J is K cross with I is J cross with K is I. Okay. And we're going to use all of that. So let's actually look at this little formula that we have down here. Okay. So watch. We're going to use all of the properties we just kind of came up with. Okay. So watch this. We have all these things that are true of the standard vectors, just thinking about the definition of the cross product. Now, what if I have a generic vector, ui plus u1i plus u2j plus u3k crossed with the other thing? Then I'm telling you what you do is you use the distributive law over and over again, yes? You use the distributive laws, okay? And for instance, like if I were to distribute u1i to here, to there, and to there, I'm going to get U1, V1, I cross I, yes? And I'm going to get U1, V2, I cross J, yeah? And I'm going to get U1 V3 I cross K. Do you see what I'm saying? I just distributed that first thing through there. And similarly with U2J, so I get U2 V1 J cross I, U2 V2 J cross J, U2 V3 J cross K, etc. Now, a lot of these things are going to go away because like I cross I, what's I cross I? That's 0, so that's gone. This guy's gone right here, yeah, because that's J cross J. This guy's gone because that's K cross K, right? What's I cross J? What is I cross J? K. All right, so I cross J is K, which is where this guy comes from. Okay. Of course, you know, this, I put the 0 vector in here just for completeness, but all three of these guys are going to go away. You see? And what is I cross K? K cross I is J. K cross I is J. That's what we had up here. But what is I cross K? Negative J, which is where this term comes from right here, right? There's a negative sign and there's a J sitting right there. Do you see that? Yeah? What about J cross I? Well, I cross J is K, so J cross I is negative K, which is where that comes from. Yeah? And let's see here. What about J cross K? Well, that's I, which is where this guy comes from. Okay, K cross I, that's J, which is where this guy comes from. And then let's see, what else do I have? K cross J is the opposite of J cross K, so that's going to be negative I, which is where this guy comes from. Okay? So once again, these 0 guys, those go away. But then what do I have? Sitting next to I have U2 V3 minus U3 V2, which is exactly what I have written right here. Okay? Okay, and then what? There's a J, like what stuff do I have attached to J? Well, I have negative U1 V3, and I have positive U3 V1. And for some reason, I've factored out a minus sign here, and you'll see why in just a minute. You factor out that minus sign, you get exactly what's written here. That's kind of the second term. And then the third term, you collect the stuff with K's attached, okay? And it's going to be U1 V2 minus U2 V1, which is exactly what we have written right here, okay? So it looks complicated, but at least, I hope it at least makes sense. We were distributing those things in there. We were using the properties that we knew, yeah? We were using the properties that we knew about these things. Now, I've kind of drawn this weird kind of symbol right here. This is a matrix. Notice that I've put the vector U right here, and I've put the vector V right here, yes? And look, would you want to memorize that obnoxious formula? Probably not. So what you do, and some of you have probably seen this before, you compute the so-called determinant. You compute the so-called determinant of this matrix. And the way you do that is you say, okay, what's going to be attached to I? And to figure out what's attached to I, you actually cross out the column and row that I is in, and you concentrate on what's left, okay? You have U2, U3, and V2, V3. And then what you do is you do this sort of thing. You go down like this, U2, V3, from upper left to lower right, and you subtract on the diagonal that goes from lower left to upper right. So U2, V3 minus V2, U3. Do you see that? U2, V3 minus V2, U3. Yeah? Okay. So basically, when you try to figure out what's sitting next to I, you get rid of the first coordinates and concentrate on just the second and third coordinates. And you do this little 2 by 2 determinant. That's what that is right there. You kind of do that little 2 by 2 determinant. Okay, so that's how you get I. Again, you kind of cross out column and row. you look at this guy right here and you go this times that, or that these two multiplied together minus these two things multiplied together. That's how you get the I term right there, okay? Now, what about the J term? Well, when you go to the J term, you actually slap on a minus sign, okay? And you cross out its column and row, and what's left? Well, everything that isn't a second coordinate, yes? And you do the same thing. You go this times this, which is U1 V3, minus this times this, which is, V1 U3, okay? And you slap on this little minus sign right there. Okay, now, to learn what's actually going on here, you take a class called linear algebra, okay? And linear algebra is really the thing that kind of describes in full geometric detail what's happening here. But in essence, what you do to figure out the sign that you attach to a term in here is you basically take row plus column. And if that's even, it's a plus. And if it's odd, it's a minus. So like if I was at position I, for instance, what row and column is that? That's row 1, column 1. Row plus column is 1 plus 1, which is 2. Is that even? Yes. So you would do a plus sign, yeah? Now what about J though? J is row 1, column what? 2. 1 plus 2 is 3, which is odd. So would you do a minus or a plus? Minus. Okay. And what about K? K is row 1, column 3. 1 plus 3 is 4, which is even. Therefore, that would come with a plus. Okay. So what you do is you go to K, cross out the third coordinates and the I and the J, and then you concentrate on these other guys and you go this times this minus this times this. Okay. You always go, upper left to lower right minus lower left to upper right. Okay. And that's where this term comes from. U1 V2 minus U2 V1. Okay. That simply helps you remember how to compute this thing. It's just an aid to memory, the determinant of this little 3x3 matrix. Okay. Put IJK in the first row, and then you put these guys right here. By the way, what I like to do sometimes is I go like this. I'll put U equal to U1, U2, U3, and V equal to V1, V2, V3. I don't even draw the matrix. What I do is I kind of already imagine this as the matrix. I've listed V below U. And then what I do is I say, okay, well, what's the first coordinate of U cross V? Okay, well, the first coordinate, I just cross out the first entries and I go this times this minus this times this, yes? So it's going to be U2 V3 minus V2 U3, comma. Yeah, what's next? Well, I cross out the second entries and I go this times that. But of course, what do I have to put in the second entry? Remember, this is important. I put a minus sign. So it's going to be minus what? U1 V3 minus V1 U3. Oops, that's not a comma. That should just be multiplication. Okay, minus V1 U3. Okay, close parentheses, comma. All right, what's the third entry going to be? Well, let me just use a different color here. Maybe I'll use black. Okay, I cross out those third entries and I go this times this minus this times that. Okay, so the third entry is U1 V2 minus V1 U2. Okay, and that is what the cross product is. So sometimes I just like to sort of put the vectors below one another and just imagine that as already being my matrix. And I just go to each one and kind of quickly do it that way. Okay, but let's actually do an example here. Okay, any questions on that little computation that we just did to get this formula? We actually have a formula now, which is nice. Yeah, this formula right here, and don't forget the length of this vector is going to be the area of the parallelogram determined by u and v. Okay. Any questions on this before we start utilizing it by way of examples and whatnot? Okay. So u equals 1, 2, 3, v equals -1, 2, 4. Okay, so I'm gonna write these up here. U equals 1, 2, 3, v equals -1, 2, 4. Okay, what is u cross v gonna be? Well, you ignore the first coordinates, right? If I want the first coordinate, you ignore the first coordinates and you go 2 times 4 minus 2 times 3. Okay, that's the first coordinate. Okay, and then it's negative. And I do the same thing by ignoring the second coordinates. It's going to be 1 times 4 minus -1 times 3. Okay, close parentheses, comma. And what's the third thing? You ignore the third coordinates here. And you go 1 times 2 minus -1 times 2. So 1 times 2 minus -1 times 2. I'm just straight up applying the formula here. 2 times 4 is 8, minus 2 times 3 is 6, right? 8 minus 6 is, what's the first coordinate going to be? 2. Okay, 1 times 4 minus -1 times 3, that's going to be 4 plus 3, which is 7. So the second coordinate is -7. Yeah? The third coordinate is going to be 2 minus -2, which is 4. Okay, so there is the cross product. And don't forget, amazingly, if I were to compute the length of this thing, it would give me the area of the parallelogram determined by u and v. Flat out, which is sort of amazing. Okay, so yeah. But I also want to show you how this thing is done. Right, I have this thing in here in matrix form as well. Okay, so let me just kind of go down here. You know, you cross out the first row and first column, and you go 2, 4, 2, 3. Right, 2 times 4 minus 2 times 3 is 8 minus 6, which is 2. You go negative, cross out the second column in the first row. You go 1, 4, -1 times 4 minus -1 times 3, okay, which gives you that second coordinate of -7. Then lastly, you cross out the last column in the first row. You go 1 times 2 minus -1 times 2, which is 2 plus 2, which is 4. That's where you get that third entry right there, 2, -7, 4. Okay? Okay. Does that make sense? Hopefully that kind of makes sense. That little computation that we've done there. Okay, any questions? Questions? Well, let's do this next little problem right here. Find a vector that is perpendicular to the plane determined by those 4 points. -1, 1, 1, 4, 4, 3, 9, and 2, -1, 10. So I'm asking you to find a vector that is perpendicular to that plane in 3-dimensional space that would have those 3 points in it, provided that those points aren't like collinear or something, okay? And I start doing a little computation here. Looks to me like what we do is we kind of imagine that this point right here is the point 1, 1, 4, okay? And I figure out what the vector is that goes to 4, 3, 9, okay? And I call that u. I call that vector u, the vector that goes from 1, 1, 4 to 4, 3, 9. And that's exactly what's being computed here. Because to figure out the coordinates of that vector, I would subtract. I would go, what's the difference in the x coordinates? What's the difference in the y coordinates? And what's the difference in the z coordinates, right? So 4 minus 1 is 3. 3 minus 1 is 2. 9 minus 4 is 5. So there's u sitting right there. Okay? And secondly, what am I doing here? So 1, 1, 4. Okay, I'm going to the other point. Okay, which is, what's the other point? 2, negative 1, 10. Okay, oops, it's supposed to be a point, not a vector yet. And I call this vector v. And again, I'm going to go terminal point minus initial point. That's why you go 2 minus 1, which is 1. Negative 1 minus 1, which is negative 2. And 10 minus 4, which is 6. That's how I get my vector v right here. Yeah? So of course, what I'm saying is there's a plane that contains all three of these points. Okay? There is a plane that contains all three of these points. And I want a vector that is perpendicular to this plane. Well, doesn't the cross product kind of do that automatically? Yeah? It's going to give me a vector that's perpendicular to both of these beginning vectors. Okay? U cross V, by the way I've drawn this, I'm thinking of U as going into the board, correct? Which way is U cross V going to point? If this was like an accurate geometric depiction here, which way is U cross V going to point? Just to make sure we're on the same page here. U is going into the board, yeah? And then I rotate my arm so I can curl my fingers towards V. Isn't it going to be going like in a downward direction, like this? Okay, it's going to be going in a downward direction. And of course, it's going to be perpendicular to both of these beginning things, and therefore perpendicular to the plane itself. So this vector right here is U cross V. V cross U would have also worked. Do you understand what I'm saying? It would have just been the opposite of U cross V, but I wanted us to think geometrically about the direction of U cross V again. Okay? So I put these things into the little matrix form that we've been using. I put 3, 2, 5 as the first vector in there after the IJK row, and 1, negative 2, 6 is the second one. How do I get this 22? Well, it's going to be 2 times 6 minus negative 2 times 5. That's the same thing as 12 plus 10. You see what I'm saying? Okay, so this 22 right here is 2 times 6 minus negative 2 times 5. Yeah, and that's how you get 22. How do I get J? Well, remember J, I always slap a minus sign on there to begin with, yeah? So the second coordinate, I slap a minus sign on, and then I go 3 times 6, okay? 3 times 6, which is 18, minus 1 times 5. 18 minus 5 is 13, and that minus sign is because I'm doing the J coordinate. Do you see? Yeah? Okay. And then finally, I'm going to go 3 times negative 2, right? So 3 times negative 2 minus 1 times 2. So 3 times negative 2 is negative 6, minus 2 is negative 8. That's where this comes from. Okay? All right, so that's what I get for my cross product. That vector will be perpendicular to the plane in hand. And that's going to be important, by the way, for when we actually start doing some geometric stuff later on with planes and lines in three-dimensional space. Okay? So that's a couple of good examples to start with. So I just want to summarize, kind of make sure we're on the same page. 1, what's the first thing we want to be true about the cross product? So if I give you two vectors, I want the cross product to be perpendicular to those. Secondly, I want the length of the cross product to be equal to what? The area of the parallelogram determined by the beginning vectors. And third, what about the direction? It's determined by the right-hand rule. Okay, so 1 needs to be perpendicular to both vectors. 2, its length needs to be equal to the area of the parallelogram determined by those. And 3, its direction needs to be determined by the right-hand rule. Okay? All of that gave birth to all of what we just did, yes? We had all those little properties. We thought about I, J, and K, and what they would, the cross products would have to be there. Thought about the distributive law and why the distributive law gives us a general formula, and the formula ends up being this guy right up here. It's just the nice formula for the cross product right here. Okay, and again, it looks gnarly. That formula looks gnarly, but it's pretty easy to remember by using the determinant of that little 3x3 matrix. Okay. So hopefully that's good. We're going to look at a lot of properties of the cross product starting tomorrow. And I think we'll finish. We'll even look at things like, you ever heard the word torque before? Torque is directly connected to the cross product. Okay? And it's actually one of the motivating reasons we define the cross product in this way. Okay? That's it.